Welcome back, everyone, to the deep dive. Today, we're going really, really deep into the history of a big one, atomism.
That's right.
We're tracing its evolution, from this kind of vague philosophical idea about what the world is made of, all the way to, the bedrock of modern science.
Yeah.
And, you guys have given us a lot to think about.
Right.
With this Stanford Encyclopedia of Philosophy entry, Atomism from the 17th to the 20th century.
And it's a really neat perspective because this isn't a deep dive into like the original papers themselves.
Right.
We're not going to be reading, snippets of Newton or Boyle.
Yeah.
This is really about how the idea itself changed over time.
Yeah.
And it's really driven by philosophy and history. Different kinds of reasoning, different kinds of evidence.
Yeah, I mean, it's a great example of how, those two things are really intertwined, science and philosophy, and how they kind of push each other along.
Yeah.
So the big question here is, how did we get from those ancient Greek philosophers, sitting around debating what reality is made of, to the point where atoms are just like a given?
Right.
Like it's something we just, take for granted in science. And I mean, it's a journey that goes from metaphysics all the way to, quantum mechanics.
Right.
So that's what we're going to try to unpack today.
It's the mission for this deep dive.
That's the deep dive.
Yeah.
So, where do we start?
Well, we've got to start in the 17th century.
Okay.
Which, when we think about atomism, the ancient Greeks obviously loom large.
Yeah.
But they don't have a lot to say that's going to be super relevant to the 17th century and beyond.
Gotcha.
So the 17th century is really where we see atomism become relevant to science.
Okay, so what's the scene there? Like what's going on with 17th century atomism?
So the big thing is what's called mechanical atomism.
Oh, okay.
And this is where you have folks like Robert Boyle.
Yeah.
Who are trying to explain the world in terms of matter and motion. Okay.
And they're really drawing an analogy between how the natural world works and how machines work.
Oh, interesting. Okay.
Because there's this move towards inert matter and its properties.
Yeah.
Rather than the sort of vitalist views, like Aristotle's forms or the alchemists' principles where you have sort of active forces within matter itself.
Right.
They're trying to get rid of those.
So, just break it down to the simplest possible.
Exactly.
Yeah.
So the core idea here is that everything is made of these indivisible atoms moving around in a void. And these atoms have what they call primary properties, things like shape and size and motion.
So it's like a really reductionist picture. Everything we see and feel and touch,
totally,
it's all just, the result of these tiny particles.
Yeah, bumping into each other.
Yeah.
Nothing else, just that.
Okay.
And this was considered the most, clear and intelligible way to understand the world.
Right.
Compared to the prevailing Aristotelian views at the time.
Yeah.
Or the more occult ideas of alchemists.
So Boyle, for instance, really felt like it was perfectly clear what it meant for an atom to have a shape and a size and, a degree of motion.
Right.
But he was very uncomfortable with the idea of ascribing other properties to these fundamental particles.
Okay.
And it's not just Boyle, but a lot of these folks who are pushing this idea, it's almost an a priori argument, based on what we can conceive of as belonging to matter itself.
Right. So if you can't picture it in your mind as a physical property, then it doesn't belong.
Yeah. It becomes very murky.
Yeah.
What does it mean for an atom to have elasticity?
Yeah.
For instance, if it's not itself made up of smaller elastic parts.
Right. Okay, so, but then how do they go from there to explaining all the complexity of the world that we see around us?
So that's where the idea of mechanical reduction comes in.
Okay.
So the thought was that all those complex properties we observe, like color or texture, or even things like taste, these are all just a result of the arrangements and the motions of the underlying atoms.
Okay.
With their primary properties.
Yeah.
And Boyle uses all sorts of analogies for this. A key fitting a lock.
Right.
The workings of a clock.
Yeah.
The idea is that the function of these macroscopic objects can be fully explained by the shapes and sizes of their parts.
Okay, like a clock's ticking is just gears of different sizes.
Exactly. Turning. Yeah, okay.
Just a matter of how those things are arranged and how they move together.
Okay, but the text points out a little problem with this.
There is a little bit of a problem.
It's like they're not really reducing things to the atomic level.
Yeah, so it's fascinating because these analogies, like the clock, they seem like really compelling reductions. but they're not actually reductions to those atomic properties like shape, size, and
Yep.
motion.
Yeah.
So for instance, if you think about that key fitting into the lock,
Right.
what's really important there is that the key is rigid
Okay.
and the lock is rigid.
And that rigidity isn't just a matter of shape and size and motion of the atoms. You know what I mean?
Yeah.
Same with the clock. The clock depends on elasticity of springs,
Yeah.
or the weight of a pendulum bob.
Mm.
These are properties beyond just the shape, size, and motion of atoms.
Yeah. Okay, so it's not a perfect reduction.
It's not a perfect reduction.
Yeah, okay. So this brings us to like a major hurdle for any kind of atomism.
Right.
Which is, how do you even get knowledge about these unseen atoms
Yeah.
from the world that we can observe?
Yeah. It's a problem.
It's a big problem, and I think the text called it the problem of transdiction.
That's right, the problem of transdiction. It's a really important epistemological challenge for atomism.
Yeah.
How do you get knowledge of something that you can't see, that you can't observe directly?
Right.
That's going to be a problem for pretty much any scientific theory that deals with unobservable entities.
Yeah.
So, Mandelbaum, who's one of the folks writing about this, he credits Boyle with proposing a solution,
Okay.
which is based on this idea of scale invariance.
Okay.
So the idea is, if some property or law is observed to apply at all levels, regardless of size,
Yeah.
we can assume it also applies to atoms.
Okay, so if gravity affects, big things and little things that we can measure,
Right.
maybe it affects atoms too.
Exactly.
But the text doesn't seem totally sold on this.
Yeah, so it's a bit tricky because it raises all these questions about what kinds of properties can we really transfer down to the atomic level.
Yeah.
So for example, like we were talking about earlier, macroscopic objects have elasticity
Right.
and divisibility,
Yeah.
which mechanical atoms were supposed to lack.
Right.
But then Boyle also attributes this property of absolute impenetrability to atoms, which no macroscopic object actually has.
Yeah, that's interesting.
So there are all sorts of these problems.
Yeah. Okay, so we've got this problem of how do we even know anything about these atoms? And then we have this other thread running through the 17th century,
Right.
which is the theory of natural minima.
Yeah.
So how does that differ?
Yeah, this is really cool because this comes out of the Aristotelian tradition.
Mm-hmm.
And so it's got a totally different starting point.
Sure.
It's primarily focused on trying to explain chemical change.
Yeah.
And Aristotle, he recognized that chemical combination was different from other kinds of change.
Yeah.
So he was looking at mixing copper and tin to make bronze.
Right.
And he's like, okay, that's not just like altering something.
Yeah.
It's not like, you take a piece of wood and you carve it into a statue.
Yeah.
The wood is still there. It's just changed shape.
Yeah.
But it's also not like complete generation and corruption where something just pops into existence or vanishes.
Right.
If you burn the wood, you get ashes and smoke,
Yeah.
but the wood is gone. Chemical combination is different because the original substances don't just disappear,
Right.
but they don't persist unchanged either.
Yeah.
So what's going on there?
Right.
That was the puzzle.
Okay, so that's what natural minima are for.
That's where natural minima come in.
Okay.
So the scholastics, they develop this idea further.
Yeah.
They say, okay, so substances have these least parts,
Yeah.
these natural minima.
Yeah.
And chemical combination happens when the minima of one substance come together with the minima of another substance,
Yeah.
and they form new minima
Okay.
that are characteristic of the compound.
Yeah.
So it's a different picture
Mm.
than the mechanical atomists.
Yeah.
Because these minima are not just like tiny billiard balls bouncing around.
Right.
They're assumed to have properties.
Yeah.
They're assumed to be changeable.
Okay.
And they retain some of the characteristics of the substances they make up.
So they're like the ingredients in a recipe?
That's a much better analogy
Yeah.
than the Lego bricks.
Yeah.
It's not just about putting things together. It's about these things transforming when they interact.
Yeah.
So there are some similarities between mechanical atomism and natural minima, but they're really coming from these radically different intellectual traditions,
Yeah.
and they have different goals.
Okay, so mechanical atomism is trying to explain like everything.
Right.
The whole
And
universe.
it's a fundamental ontology.
Yeah.
What's the world made of?
Yeah.
That's the question.
Yeah.
What are the fundamental building blocks of reality?
Yeah. And natural minima is more about like specifically chemistry.
Yeah.
How do we understand chemical change?
Yeah. Okay.
So it's not about like the grand picture of the universe. It's about explaining this specific set of phenomena.
Okay, so it's really interesting. You've got these two competing theories,
Yeah.
but then the text also talks about eclecticism.
Yeah.
So what's going on there?
So it's really neat because as the emphasis on experiment grows in the 17th century, the atomists become less rigid in terms of sticking to their philosophical systems.
So you see people borrowing ideas from both traditions,
Huh.
trying to explain specific phenomena.
Okay.
So even Boyle, Mr. Mechanical Atomism,
Right.
he initially calls his atoms natural minima.
Oh, wow.
And he even attributes properties to them based on the substances they belong to.
Yeah.
So he's clearly borrowing from Sennert, who was a big proponent of natural minima.
Okay.
So it's a really neat period because it's showing a shift toward trying to make these atomistic ideas relevant to what people are seeing in the lab.
Yeah.
Even though the experimental basis for atomism itself is still pretty weak.
Okay, so the 17th century is really laying the groundwork.
It's laying the groundwork.
Yeah. But then we move into the 18th century,
Yeah.
and we get Newtonian atomism.
That's right.
So how does Newton build on these earlier ideas?
So what Newton does is he takes mechanical atomism and he gives it a Newtonian makeover.
Okay. Yeah.
He brings in his laws of motion, he brings in the concept of inertia,
Okay.
and he applies it to those little mechanical atoms.
Yeah.
So we're still talking about hard, impenetrable, movable particles.
Mm.
But now they have inertia. Now they're governed by these precise laws of motion.
Yeah.
And that gives us a much more rigorous framework for thinking about how these atoms might behave.
Okay, so it's mechanical atomism, but with Newton's, physics engine.
That's a great way to put it.
Yeah. Okay, and so what else? Does he make any other changes?
Yeah, so one really interesting thing is that Newton, he proposes this idea of a single homogeneous matter.
Oh.
So all matter is fundamentally the same.
Oh.
You realize that atoms are really, really tiny.
Okay.
And most of matter is just empty space.
Yeah. Okay, so far so good. But the text mentions this kind of philosophical tension
Yeah.
with Newton's introduction of force.
Right.
Especially gravity. So how does that complicate things?
Yeah, so this is really interesting because the mechanical philosophers, they were all about getting rid of any kind of spooky occult forces.
Right.
They wanted to explain everything in terms of contact and motion, the shape, size, and motion of atoms.
Yeah.
That was the goal.
Yeah.
So when Newton comes along and says, well, actually, gravity is this fundamental force,
Yeah.
it's not reducible to contact and motion.
Yeah.
It acts at a distance.
Yeah.
This really rubs some people the wrong way.
Yeah. Okay.
It's not just that they don't like the idea of action at a distance.
Yeah.
I mean, Newton didn't like that either.
Right.
But what really bothered them is that Newton explicitly rejects the idea that gravity is essential to matter. So he's saying, look, gravity exists. It's real. It's doing all this stuff.
Yeah.
But it's not part of the essence of matter itself. It's something added on.
Okay, so for someone who's really into the purity of that mechanical philosophy,
Totally.
it kind of feels like cheating.
Totally. It's like, okay, you're smuggling in this weird, spooky force
Yeah.
that you can't explain in terms of our nice, clean mechanical principles.
Right. Okay. So what about things like chemical reactions? Did Newtonian atomism have anything to say about those?
Yeah, so they tried to use forces to explain things like elasticity and chemical affinities.
Okay.
So the idea was that the least parts of chemicals would have these forces of affinity between them.
Okay.
And the strength of these forces would determine whether or not the chemicals would react.
Yeah.
But this didn't really lead to any new predictions in chemistry.
Okay.
Right.
Right.
So it was kind of just taking what they already knew about how chemicals behaved
Yeah.
and projecting that onto the atoms. So it wasn't a very fruitful approach.
Okay. But that doesn't mean they gave up on atomism completely, right?
No, not at all.
I mean, what about Newton's work on optics?
Yeah, so Newton's work on optics is really interesting because he does talk about light as being made of particles.
Okay.
So he's using an atomistic model.
Yeah.
But those particles aren't really atoms in the same way that we've been talking about.
Okay. Yeah.
They have these weird forces.
Yeah.
They have all these properties that are kind of ad hoc.
Okay.
It's not really clear how they fit into this grand mechanical picture.
Okay, so it's kind of like atomism light.
It's atomism light.
Yeah.
And that's kind of the story of 18th century atomism in general. You have a lot of people paying lip service to it. They're saying, oh yeah, Newton was right, atoms are real. But the actual experimental work,
Yeah.
especially in chemistry, it's really progressing independently of these atomistic ideas.
Okay.
So you've got folks like Jeffrey who's making these affinity tables just based on observation.
Yeah.
What substances combine with each other, what substances can be recovered from each other.
Right.
And Lavoisier comes along.
Yeah.
And he's really focused on identifying elements.
Yeah.
What can't be broken down further.
Yeah.
So these are all very empirical approaches.
Yeah.
And they're not really driven by atomistic speculation.
Okay, so we get to the 19th century.
Right.
And we have Dalton.
Yeah.
And finally, we get some real chemical atomism.
That's right.
So what's so revolutionary about his approach?
So what Dalton does that's really groundbreaking
Yeah.
is he links experimental measurements, specifically these combining weights,
Okay.
to an actual property of atoms, their weight.
Okay.
So for the first time, it seems like you can move from lab data to something concrete about these little particles.
Right.
And this is a huge shift philosophically because it's grounding atomism in empirical observation
Yeah.
rather than just these a priori arguments
Yeah.
about what's intelligible.
Okay, so what are the core ideas here? What's he actually saying about atoms?
So he starts with this idea that elements are made up of these ultimate particles,
Yeah.
atoms,
Yeah.
and compounds are formed by specific combinations of these atoms,
Okay.
which he calls compound atoms.
Compound atoms, okay.
Right.
Yeah.
And he also makes this crucial assumption that all atoms of a given element are identical.
Okay.
So all hydrogen atoms have the same weight, all oxygen atoms have the same weight.
Okay.
And that immediately explains the law of constant proportions.
Okay, how so?
So if you take water, for example,
Yeah.
if every water molecule always contains a fixed number of hydrogen atoms with a certain weight and a fixed number of oxygen atoms with a certain weight,
Yeah.
then the ratio of the weights of hydrogen to oxygen in water will always be the same.
Yeah. Okay, that makes sense.
Right.
Yeah.
So it's a really simple, elegant explanation for this fundamental chemical observation.
Okay, so by measuring the weights of things combining in the lab, you can start to work backward and figure out
Going backward.
the weights of the atoms themselves.
Exactly.
But the text mentions this underdetermination problem.
Right.
What's that all about?
Yeah, so this is a really important point to understand about early Daltonian atomism,
Okay.
because even though he's got this brilliant idea of combining weights to atomic weights,
Yeah.
there's still this problem of figuring out the exact ratios of atoms in a compound.
Okay.
So for instance, if you find that a certain weight of element A combines with a certain weight of element B to form a compound,
Yeah.
you don't know immediately
Right.
whether the ratio of A atoms to B atoms is 1-to-1
Okay.
or 2-to-1 or 1-to-2.
Right.
So it could be AB, A to B, AB to. You see the problem.
Yeah.
And this is the underdetermination problem.
Yeah.
So Dalton tries to solve this with what he calls the simplicity assumption. So he says, well, when only one compound of two elements is known, we should just assume it has the simplest formula, usually AB.
Right.
But that's clearly an arbitrary assumption.
Yeah.
And it often led to incorrect formulas
Yeah.
and incorrect atomic weights.
Right.
So even with this brilliant new connection to experimental data,
Yeah.
there's still a lot of guesswork involved in figuring out these atomic ratios.
Okay, so it's a step in the right direction, but it's not a complete solution.
Exactly.
So what about some of the other things that were going on in chemistry at the time? Like, I think there was this guy, Gay-Lussac.
Right.
He's doing some interesting work with gases.
Yeah, so Gay-Lussac comes along, and he's observing the volumes of gases that combine in chemical reactions.
Okay.
And he finds this really interesting law,
Okay.
which is that the volume ratios of reacting gases are always simple whole numbers,
Okay.
provided that the temperature and pressure are the same.
Okay. So for example.
So for instance, one volume of oxygen combines with 2 volumes of hydrogen to form 2 volumes of water vapor.
Okay, that's interesting.
Right.
Yeah.
So if you're thinking about atoms,
Yeah.
this suggests there's some kind of direct relationship between the volumes of reacting gases and the numbers of atoms or molecules involved.
Yeah.
So this leads to Avogadro's hypothesis,
Okay.
which says that equal volumes of gases at the same temperature and pressure contain equal numbers of atoms or molecules,
Yeah.
which kind of makes sense intuitively. Right.
Right. Yeah.
But if you take this together with Dalton's idea of indivisible atoms, you run into a problem.
Okay.
Because it seems to imply that in some reactions, atoms are being split.
Okay.
So for instance, going back to the water example,
Right.
the fact that you get 2 volumes of water vapor from 1 volume of oxygen suggests that the oxygen atom is being divided in half.
Okay.
But Dalton really resisted this idea.
Right.
Because his whole concept was based on the indivisibility of atoms.
Right.
So this created a real tension between these different observations and how they fit together.
Okay, so was Dalton's theory, like, immediately accepted by everybody? Or was there still some skepticism about the reality of these atoms?
No, there was definitely skepticism,
Okay.
even among chemists.
Right.
And that's because, a lot of folks felt like Dalton's theory was useful,
Okay.
but they weren't convinced that it was actually proving the existence of atoms.
Okay.
So, for example, Berzelius, who was a really influential chemist at the time,
Yeah.
he develops this whole system of chemical formulas,
Okay.
which are really good at representing combining weights
Right.
without actually invoking atoms.
Okay, so you can do the chemistry without having to believe in the atoms.
Exactly.
Okay.
So he says, look, these formulas are doing all the work.
Yeah.
Why do we need this extra hypothetical layer of atoms?
Right.
And so that was a big debate at the time.
Yeah.
Like, is Dalton's theory actually giving us a deepened understanding of what's going on?
Yeah.
Or is it just a useful tool for calculation?
Yeah, it's a really interesting question. So then what about organic chemistry? How did that fit into all of this?
Yeah, so organic chemistry explodes in the 19th century.
Okay.
They're discovering all these new carbon-based compounds.
Yeah.
And it quickly becomes clear that just knowing the proportions of elements in a compound isn't enough to identify it or predict its properties.
Okay.
Because you can have all sorts of different compounds
Right.
with the same elemental composition, but they behave very differently.
Okay.
So chemists start to use what they call rational formulas,
Okay.
where the arrangement of symbols in the formula actually reflects something about how the compound behaves chemically.
So the structure of the molecule becomes important?
The structure becomes crucial.
Yeah.
So you can represent things like the replacement of one element by another in a reaction, or the persistence of certain groups of atoms through a series of transformations.
Okay.
And this really helps them to make sense of this huge diversity of organic compounds. And by the 1860s, with the idea of the tetravalent carbon atom,
Right.
the fact that carbon can form these long chains,
Right.
these rational formulas become increasingly detailed.
Okay.
And importantly, they become more or less unique for each compound.
Okay.
So you have a one-to-one correspondence between the formula and the substance.
Okay, so organic chemistry is kind of solving this underdetermination problem
Totally.
without needing to talk about atoms.
Right. So this is really interesting because folks like Duhem use this to argue that chemistry is actually independent of atomism.
Okay.
It doesn't support atomism.
Okay.
He's like, look, these chemists are not talking about atoms.
Right.
They're talking of combining volumes or portions or proportions. They're not committing to the reality of these little particles.
Right.
And they're doing fine.
Yeah.
Their formulas are working.
Yeah.
They're explaining stuff.
Yeah.
They're predicting new compounds.
Yeah.
So why do we need atoms?
Oh.
And so that's a really powerful argument.
Okay. But didn't they start talking about chemical atoms at some point?
Yeah, so this is where it gets really nuanced.
Okay.
Because when chemists start talking about chemical atoms,
Yeah.
they're not necessarily thinking about these like tiny billiard balls bouncing around.
Okay.
It's more of a concept.
Okay.
It's a way to think about how elements combine
Yeah.
based on their combining power or valence.
Okay.
So it's like a model for explaining chemical behavior.
Yeah.
Even if you're not sure what these atoms physically are.
Right.
So it's very different from the physical atoms that the mechanical philosophers were talking about.
Okay. So the chemical atoms are they're defined by their chemical behavior.
Exactly. So
Yeah.
they're not just these little bits of matter with primary properties.
Yeah.
They have properties that are specific to their chemical interactions.
Yeah. Okay.
And this is what